So in this last video of this lecture, I'm going to derive the harmonic oscillator wave functions, but I will do so without even writing down the Schrödinger equation. We will rely entirely on the solution, that algebraic solution I presented, that took advantage of the creation and annihilation operators. It turns out that they are very helpful in determining the explicit form of the oscillator wave functions, psi of x. So, but before we write down these wave functions, we derive these wave functions, let me summarize what we know so far, which is actually a lot. So, first of all, we found a way to represent the harmonic oscillator Hamiltonian in this compact form in terms of these creation annihilation operators here. And using the algebra or the commutation relations of this harmonic oscillator operators, we derived the energy spectrum of the oscillator, which has this form, h omega n plus 1/2, where n is equal to 0, 1, 2, etc. So, again, I reiterate that this spectrum is special in that the level spacing between the neighboring levels is always the same. So it doesn't change as we go higher up in energy. So another thing we derived, and so here I'm being a little more specific, is that given an arbitrary eigenstate of the Hamiltonian with the quantum number n, as here, so we can generate the entire spectrum by applying the creation operators and annihilation operators. The creation operators raise the energy of the system by h omega, so we go from n to n plus 1, and in the case of normalized eigenfunctions, there appears this coefficient. I haven't derived it in the previous video, but this is rather straightforward to do so using the same methods, and it's done in many textbooks, so I'm not going to spend time on that. And likewise, given the same eigenstate n, we can find the eigenstate corresponding to a lower energy with one less quantum of h omega by applying these annihilation operators. But what we don't know at this stage, we don't know an example of any wave function, explicit wave function. So, and preferably we would like to see a wave function, let's say in real space, which is more intuitive than other sort of, let's say, abstract spaces that we have been operating with so far in this problem. So, in order to find the explicit form of an eigenfunction, let me actually focus on the ground state, that is the lowest energy state in our problem. And this eigenstate, as we discussed in the previous video, is characterized by the fact that the action of this A dagger A on it gives simply 0. So it gives us, it's an eigenstate with an eigenvalue 0, or the eigenenergy of this state is equal to h omega over 2. So in other words, so the annihilation operator acting on this state must produce 0. And we can, write this annihilation operator explicitly in real space. So we use the definition, if you want, of this A as so. And here what I'm going to do, I'm going to just write down explicitly the form of the momentum operator and position operator. So in real space, the position operator is really simple. It's just the multiplication operator, while the momentum operator, as we know, is just minus I h bar d over dx. So therefore, here I will have simply, I will just simply remove the imaginary constant. So all in all, the equation, so I should have written perhaps here psi naught, because I'm specifically talking about the ground state of the harmonic oscillator. So explicitly, the equation for this psi naught, therefore, becomes the following. So we'll have this square root of m omega over 2h bar x plus h over 2m omega h bar in the denominator d over dx. So which is coming from this momentum operator. And this acts on psi naught, and this whole thing must be equal to 0. So here what I'm going to do, I'm going to, simplify this thing a little bit. So I'm going to put the square root here on top. I'm going to get rid of the factor 2. And so what I see here is that I can introduce a new parameter let me call it x naught, which is the square root of h divided by m omega, and it appears both here and here. And so this, you can check that the physical dimension of this square root of h over m omega is a length scale, so it has a physical dimension of length. So this is in some sense a natural length scale for the harmonic oscillator problem. And so it is convenient, therefore, for me to rewrite my equation as above in the following form. I will write it as x over x naught plus x naught times d over dx. And this whole thing acts on the wave function psi of x, and we want to produce 0. So now let me just rewrite this equation in a slightly different form. So I'm going to write d over dx is psi prime. So this is going to be psi prime. Put this guy in the left-hand side. So I'm going to have minus x over x naught squared times psi. And so I just want to solve this differential equation. And you can check, you can solve it formally, or you can just convince yourself that the solution to this equation is an exponential, it's a Gaussian, basically, minus x squared over 2x naught squared. So, and this is, let me just put zeros in here, which correspond again to the ground state. And this is pretty much the result. So C here is a coefficient which is determined by the normalization of this wave function. So again, this wave function describes a particle in the ground state of the harmonic oscillator. And so therefore, you know, the total probability for me of finding a particle somewhere in space must be equal to 1. So therefore, this integral from minus infinity to plus infinity of psi naught squared, so I don't bother here with the complex signs because everything is real so far. So this must be equal to 1, and this gives me the value of the wave of this coefficient that multiplies this ground state wave function. So I can just let me just write it down. So this C is equal to m omega over 2. Pi. That is pi h bar to the power 1/4. So this is the normalization coefficient. But notice that we have found the ground state wave function without actually solving the Schrödinger equation. We actually solved a much simpler equation, this first order differential equation, just by requiring that our wave function is an eigenstate with an eigenvalue 0 of this annihilation operator. Okay, so this is great. So we can now work with this wave function if we want, but what about the higher energy states? So what we have just done was we determined this guy, the lowest energy state. So here what I'm showing, let me just write down. So this is first of all the potential to this v of x, so this is x, and this these levels here correspond to the energy levels of the harmonic oscillator. And the lowest energy has the wave function as so, which is a usual Gaussian. So this is a typical Gaussian. And higher energy states have a more complicated sort of texture. So how do we get these eigenstates? Well, so here we can take advantage again of the creation operators now. So for as we discussed in the first slide in this video, so the relation between the low energy states and high energy states, so let's say to go from n to n plus 1, we can simply apply the creation operator divided by n plus 1, square root of n plus 1. So if we apply it to our eigen state n, we're going to get, there is no square root here, it's just n plus 1, a normalized state which corresponds to high energy. And so what we can do, we can apply these operators, let's say, to our ground state. So we can apply this guy as many times as we want to the ground state. For instance, we can generate this wave function. So by just applying this derivative essentially to the Gaussian. And this will produce certain coefficients in front of the Gaussian. And these, well, not coefficients, I would better to say polynomials, which are functions of x. And these guys, these polynomials, they are called Hermite polynomials, which are special functions, and you can Google them, or you can look them up in Wikipedia and in many books. So this sort of this solution using the explicit form of the wave functions and the explicit form of the Hermite polynomials appears in pretty much any book on quantum physics. And I'm not going to spend time on discussing these details. I will simply notice that, well, you can actually solve the Schrödinger equation starting from the spectrum up to the ground state and up to the excited states using only the creation and annihilation operators. So there is very little insight that is actually needed from the Schrödinger equation, which is in fact quite remarkable. So in your homework, you will need to play around a little bit with these creation annihilation operators and with this ground state wave function. And I hope that you found this solution illuminating. And of course, I encourage you to look into the literature to see more about this very important problem of quantum physics.